Welcome to the series Getting Started Reinforced Concrete Building Design with Revit. In this tutorial, a simple building will be modeled using Autodesk Revit as the BIM platform. The structural design will be carried out with the SOFiSTiK software suite. The series is organized into 4 parts. Firstly, the building will be modeled as a physical model in Revit while getting familiar with the core platform functionalities. Next, an analytical model will be derived from the physical model in just a few clicks using the SOFiSTiK Analytical Model Generator, or in short, SOFiSTiK AMG. All relevant information, geometry, materials and more will be captured and linked automatically. In the third step, the model will be refined using SOFiSTiK Analysis and Design. Actions, loads, cross-sections and materials will be reviewed and members positioned inside Revit. Finally, the model will be exported to the SOFiSTiK Structural Desktop, or in short, SSD, to mesh the structure and perform structural analysis, designs and checks. The objective is to enable structural engineers to learn Revit's fundamentals and confidently create or edit simple models. The focus remains on the essentials to keep things concise. For day-to-day production work, an in-depth course is recommended to master Revit and adopt BIM workflows effectively across projects and organizations. Our subsidiary BIMotion is the perfect partner for this. We will model a 3-story reinforced concrete building with overall dimensions of roughly 20 by 9 meters. It is resting on a foundation slab, has a flat roof, and includes all basic structural elements: walls, columns, beams, and slabs. A plan drawing with the details is part of the appendix. Let's start a new project and select an appropriate template, in this case, Structural Analysis Default Metric Up, which can be found in the generic English content package. Please bear in mind, a template provides pre-configurations such as views, component families and more, allowing us to get to modeling faster than starting from scratch. When using a different template, the necessary steps might differ slightly. On first glance, we notice a ribbon in the upper part of the screen. This is where most Revit commands can be found, divided by categories. Many plugins, such as SOFiSTiK Analysis and Design, have their own ribbon tab. Revit supports multiple disciplines, but for structural engineering, the focus is on the structure discipline, where all load-bearing components are found. To tidy up the user interface, unnecessary disciplines can be deactivated under File, Options, Interface. On the tab Manage under Settings, we can find the project units. For example, let's change the measurement for length from millimeters to meters and add 2 decimals and make sure to activate the unit symbol to avoid confusion. Under View User Interface, we can find the Properties palette, which shows the selected object's properties. With nothing selected, the properties apply to the active view. Next, we also activate the project browser, which allows to navigate between views, schedules and sheets. To tidy up the project, unnecessary elements are removed. The largest part of the screen is occupied by so-called view panels. It is possible to have multiple views open at once, which we will make use of now. The Active View tab is highlighted and is also shown in bold in the project browser. We create a 3D view with the appropriate shortcut in the Quick Access toolbar at the very top, then open the South Elevation and substitute Structural Plan Level 2 for Level 1. Let's arrange these views with the command Tile Views on the ribbon tab View Windows. Double-click the mouse wheel to center and zoom to extents. In the elevation view, we can select the existing Level 2. With the command Copy on the Modify tab, we can create additional levels by moving the cursor upwards and placing them at the desired distance. Using the keyboard to enter the exact values is the fastest and safest method to do this precisely. Next, we are going to create the missing structural plans for the new levels. Additionally, we want to create floor plans for each level as well. To determine their differences, let's have a look at the following slides. Both structural plans and floor plans reference building levels, but differ in the viewing direction. We understand structural plans to look from below upward, representing the engineer's perspective, while floor plans look from above downward, which is the architect's view. This distinction is visible in the type properties of each view. Structural plans are preferred for modeling tasks in this tutorial. To clarify this distinction, the views are renamed. For the structural plans, Level 1 becomes Level 1 Foundation, Level 2 becomes Level 2 Ceiling First Floor, and so on. In neither case do we want to rename the referenced level accordingly. The changes are just for the view names. Floor names will be renamed to Level 1 First Floor, Level 2 Second Floor, and so on. Let's make sure to save the project regularly to avoid loss of data, in case something happens. In Structural Plan Level 1 Foundation, we will now define the grid. First, place a horizontal grid line and copy it at 3 meters distance. Repeat twice more and see the automatic numbering going up. For the vertical grids, we will use letters, so create one and immediately rename it to A. Then go ahead and copy it with spacings of 3 times 3.5 meters, 5 meters and 4.5 meters. Here too, the grids will automatically be named with the right syntax. Adjust the length of the grids as needed. For grids to be shown in views, the following settings are required. We open Visibility Graphic Overrides, which are accessible through the View tab, the View Properties, or most conveniently, the keyboard shortcut VV. Then we go to Annotations Category tab and make sure the grids category is checked. Additionally, for 3D views, we must define at which level the grids are displayed. To do this, go to Show Grids in the View Properties and select at least one level. Now we are going to place structural walls. We choose Wall on the tab Structure to create load-bearing walls. The Properties panel changes and we can select the appropriate family type from the drop-down menu. Because it doesn't exist yet, we choose Generic 200 mm as our starting point and go to Edit Type. We will duplicate this existing type and rename it. As a pattern, we recommend something like material and thickness. Next, we edit the structure where we can specify its layers. The thickness is 250 mm and the material is a concrete of the quality C3037. To do that, we first select the material and then switch its material asset physical to C3037 with a compression strength of 30 MPa. Finally, let's make sure the name is correct. Once the family type is set, we can start modeling. We are working in a structural plan level 1, so we want to make sure we place the walls from level 1 upwards by selecting height and level 2 as the upper end. We place the first wall at 0.5 meters from the corner and can immediately continue because the chain command is on. After the second wall is placed, we use escape once to cancel the chain. A second escape would cancel the command entirely, which is not what we want here. Next, we go to the other corner and do the same. But instead of using the cursor to find the right position for the starting point, we use the keyboard instead. This is always possible when a temporary dimension is shown. Let's continue with the right-hand side building part consisting of the 4 outer walls and the 3 interior ones. Exterior columns are next, with dimensions of 1 meter by 25 centimeters. Because no such type exists, we repeat the steps from the wall to create a new type by duplicating an existing one. The column is then placed at the grid intersections. The auto snap helps us here to be precise. In the 3D view, a mistake becomes apparent. The column was modeled downward due to an incorrect level reference. This is quickly corrected by setting the top level to level 2 and removing the offset. The 3D model updates in real time. Next, the interior columns. Looking at the family types in the project, we see that no round columns exist. To add one, we go to Insert Load Autodesk Family and find such a family in the Structural Column category. We quickly duplicate the type and modify the dimensions. For this family, the material is an instance parameter, so it can be found on the individual columns and not as a part of the family type. We place the columns on the grid, this time with careful attention to the level reference, modeling upward to level 2. Because we forgot the 2 exterior columns on grid A earlier, we add them now. To rotate the column, we press space before placing them. Back in the structural plan, we are creating beams next by selecting a concrete beam as our starting point. As before, we create a duplicate and adapt the dimensions to 25 by 50 centimeters, then span it across the supports. In the 3D view, we can see that we placed them in the wrong level again. To change this, select the beams, go to Edit Work Plane and select Level 2. In Revit, there are multiple distinct ways in modeling openings for slabs and walls, each with their own pros and cons. For the wall openings, we use the method of placing components on the walls. To be able to do so, we need to add the component to the project by selecting it from the online library, like we did with columns. Depending on the content package, different components are available. Some even come with extra perks, such as drop shadows for the elements when placed in a 3D view. Once imported, we go to Component, Place Component and have a type of this newly imported opening already selected. We adapt the dimensions and place the openings roughly at the right spot and, where applicable, later move them to the precise locations. With a press of Enter, we can restart the command to place the 2 missing corridor doors. Let's adjust the width before placing them centrally between the grids. At last, we want to place the window openings. We restart the command, adjust the dimensions, and make sure to set the elevation offset at 1.2 meters. When we place the component, we see it correctly show up in the 3D view, but not on the structural plan. Instead, a warning appears indicating that the element is not visible in the current view. This is expected as the view depth does not reach the component. To help understand the view depth, we look at the following slides. This elevation shows a side view of a lower wall with several openings and a ceiling, as well as a window opening in the upper wall. Only elements within the view range will be visible in the structural plan that is looking upwards. To adjust these settings, we go to View Range in the View Properties. A helpful tip: when having problems selecting the right thing, the Tab key allows to cycle through overlapping objects in a view. We repeat this process on the other wall by placing the component. To create additional objects on the same host, we can also use the copy command. Now let's create a foundation slab. We go to level 1 and choose structural floor. We repeat the creation of a new family type with thickness 250 mm, sketch the boundary and set the span direction to the short side of the slab. In the structural plan, which is looking upwards, we check the view range again and set the cut plane to 30 cm below the reference level. Elements above the cut will now appear dashed, which stands for hidden lines. This matches the expectation for viewing from below through the slab. With the regular story complete, we copy its elements to the next level. To do so, we select all relevant elements in a suitable view. Let's filter out all unwanted elements by deselecting grids, then click Copy and finally Paste align to selected levels and choose Level 2. In the upper story, adjust the floor thickness to 200 mm instead of 250 by creating a new family type. Finally, we copy the already selected slab to level 3 and open the corresponding floor plan. As our next step, we add the slab openings for the staircase or elevator. To do so, we could insert more opening components like we did for walls. Instead, I want to show two different methods. One way would be to use opening vertical on the structural tab and define its dimensions, but we would need to do this for each level individually. Alternatively, we are going to use opening shaft, adjust the size according to the provided plan, and make sure to apply the base and top constraints correctly. To check that it worked, we can turn the 3D view in a wireframe for a second. For the top story, it is comfortable to stay in level 3, third floor, and model upward to level 4, so the geometry is visible while drawing. We are going to create the exterior walls from level 3 as base to level 4 as top along the grid. Next, we place columns size 250 by 250 millimeters on the grid. We insert the top floor beam on level 4, spanning from columns to the walls. Then we model the level 4 slab with a thickness of 250 millimeters, using temporary dimensions to set its length to 13.75 meters, measured from the exterior face. Thank you for watching. Stay tuned for the next part of this series.